Hello there, welcome to the channel. Before we begin the video, if you haven't subscribed to our channel yet, please do subscribe and hit the bell icon. So here is a question. The lowest eigenvalue of the 2 by 2 matrix is, so the matrix is given 4, 2, 1, 3. You have to find the lowest eigenvalue. Now traditionally how will we go about finding out eigenvalues is by doing determinant A minus lambda I equal to 0. This is the characteristic equation, determinant A minus lambda equal to 0. And so for this matrix it would be 4 minus lambda, 2, 1 and 3 minus lambda. This determinant equal to 0. We will just expand it, get a quadratic, solve it, and those will be the eigenvalues. There is also another way of doing it, which is by using the properties of eigenvalues. So one of the properties of eigenvalues is that the sum of the eigenvalues is a trace of the matrix. So the trace is nothing but the sum of elements on the principal diagonal, which is in this case 4 and 3. So the sum of eigenvalues should be 4 and 3, that is going to be equal to 7. And the product of the eigenvalues is the another property. Product of eigenvalues is the determinant of the it is a determinant of the matrix. So what is the determinant in this case? It is 12 minus 2, which is 10. So now all we need to do is find out two such numbers which have the sum as 7 and product as 10. Quite simple, the numbers are 2 and 5, right? And we have to select the lowest one. So the lower of the two is 2. So the answer for this question will be 2. We move on to the next question. It asks us what is the condition for which the eigenvalues of this matrix will be positive. Okay, so we have just discussed that the product of eigenvalues is nothing but the determinant of the matrix. So the determinant is 2, 1, 1 and k. So this is going to be 2k minus 1. Now if the eigenvalues are supposed to be positive, then this product will also be positive, obviously. If two numbers are positive, and then their product is also going to be positive. So we will say, since eigenvalues are positive, their product 2k minus 1 should be greater than 0. And so this gives us k should be more than half. So we have that as option A. So here is another question. It is asking us to find out the product of the eigenvalues of this matrix. So we have discussed it now. Product of eigenvalues is nothing but the determinant of the matrix. So expanding by the first row, it is going to be 2 times 3 minus 6 plus 1 time 8. So this is 2 into minus 3 minus 6 plus 8. So the answer will be 2. So the product of eigenvalues for this matrix will be 2. So important to remember these two properties, especially that the sum of eigenvalues is equal to the trace of the matrix, and trace is nothing but sum of elements on the principal diagonal, and the product of eigenvalues is the determinant of the matrix. Remember these two properties very well, it will be helpful. Now coming to the next question, it is saying consider the matrix which is given to us 3 by 3. To find out the number of distinct eigenvalues of P. Okay, so here comes another sort of property of eigenvalues. Then whenever you have a triangular matrix, for any triangular matrix, the eigenvalues are the elements on principal diagonal. So what are the elements on the principal diagonal this time? It is 1, 1 and 1. So there are 3 eigenvalues. Any 3 by 3 matrix will have 3 eigenvalues, but then this is a case of a repeated eigenvalues. This is a case of repeated eigenvalues. So the distinct eigenvalues that P has is only 1. Alright, so the number of distinct eigenvalues is 1 and the value itself is 1. It is a repeated value. Okay, so for any triangular matrix, eigenvalues are the elements on the principal diagonal. Coming to the next question. So in the matrix equation Ax equal to R, we are given matrix A and vectors x and r. One of the eigenvalues of matrix A is, okay, so this is coming from the definition of eigenvalues. So how are eigenvalues and eigenvectors defined is that Ax equal to lambda x. So if we have any non-zero vector x, this is the definition of eigenvalue and eigenvector. For any non-zero vector x, if there exists a value lambda such that Ax is equal to lambda x, then we say that x is the eigenvector associated with eigenvalue lambda. So basically, if there is any non-zero vector x and we have an equation which is satisfied, that is Ax equal to lambda x, then lambda is the eigenvalue and x is the eigenvector. So here we are asked what is the one of the eigenvalue of this matrix. So if you observe, we are having Ax equal to r is this equation, right? So can we just try to get it in this form, that is Ax equal to lambda x. So obviously Ax is a multiplication. Now r, can r be expressed as some lambda into x? Can r be expressed as some lambda into x? So we have, this is 32, 16 and 64, and we have x as 2, 1 and 4. So can you see this? This is 2 multiplied by 16, this is 1, 16 and 4 multiplied by 16. So clearly this is, r is nothing but 16 times x. So we have r is nothing but 16x, and so we are having an equation that is Ax equal to r, but r is nothing but 16x. So we are having an equation which is getting satisfied as this, Ax equal to 16x. So 16 is the eigenvalue of this matrix. 16 is one of the eigenvalues of this matrix. We don't have to do all the calculation for 3 by 3 matrix, that is by doing the characteristic equation. It is based on the definition of eigenvalues and eigenvectors. Alright. Okay. Consider a vector p in two-dimensional space. Let its direction counterclockwise with the positive x-axis be theta. Let p be an eigenvector of a 2 by 2 matrix A with corresponding eigenvalue lambda such that lambda is greater than 0. If we denote the magnitude of any vector v by this sign, identify the valid statement regarding p where p prime is a into p. So p is what? P is nothing but, what is p? P is a eigenvector. P is an eigenvector of matrix A. P is the eigenvector of matrix A. So by definition, Ax equal to lambda x, right? For eigenvalues and eigenvectors, Ax equal to lambda x. So here what are we having is AP will be equal to lambda times p. I'm just replacing x by p because they are denoting eigenvector with p. So we should have AP equal to lambda p. Alright. So which of the following statements is valid? Okay. So it is asking about direction and magnitude. Okay. So what is happening to magnitude of p prime? So p prime is nothing but a into p. So this itself is p prime then. So we have p prime, that is a into p, which is by definition of eigenvector lambda into p. So p prime is a lambda p. So what will happen to magnitude of p prime? It will become lambda times magnitude of p. It will be lambda times magnitude of p. Quite simple. So the magnitude will be lambda times p. So of this we have two options are eliminated, a and d. The remaining two are c and b. B and c are the two options which have that. Now what is the difference is the direction. So always remember this. So always remember, whenever you have a vector being multiplied by a scalar, it does not change the direction of the vector. It never changes the direction of the vector. So even in the previous question which we just saw, whether you plot this vector or you plot this vector, they are both going to be in the same direction, just their magnitudes are different, right? So the magnitude of this vector is 16 times that of this. Similarly, over here also, the magnitude of p prime will be lambda times magnitude of p. But the direction of p prime and p will be exactly same. Right? The directions don't change whenever you multiply a vector with a scalar. So the direction will be theta, whereas the magnitude will be lambda times p. So this is the answer for this question. Consider an n cross n matrix A and a non-zero n cross 1 vector P, their product AP is alpha square P, where alpha belongs to R and alpha is not equal to, or it does not belong to, -1, 0 and 1. Based on the given information, what is the eigenvalue of A square? Okay. So once again, it is revolving around the definition of eigenvalue, eigenvector. So by definition, we have Ax equal to lambda x, right? Now here what it says is P is a vector and AP is alpha square P. So AP is alpha square P. So just compare with the definition. So what do we have? The eigenvector is P, and what will be the eigenvalue then? So the eigenvalue, we have the eigenvalue of A is alpha square, not alpha, it is alpha square. Alright, and then we are asked to find out the eigenvalue of A square. Okay, so once again comes the property of eigenvalues. So eigenvalue of A square will be alpha square square, which is alpha raised to 4. So the answer is this. Where is this coming from? This is a property of eigenvalues, that if lambda is an eigenvalue of matrix A, then lambda raised to k will be eigenvalue of matrix A raised to k. So A raised to k will have its eigenvalue as lambda raised to k. Alright. So we have it quite easily over here. Eigenvalue of A square will be eigenvalue of A squared, that is alpha square square, alpha raised to 4. Consider the matrix A, which is given to us, whose eigenvectors corresponding to eigenvalues lambda 1 and lambda 2 are in this form. We have to find out the value of x1 transpose x2. Okay, so first of all, when you come across such a thing, that is x1 transpose x2, where x1 and x2 are two vectors. So let's just quickly take an example. So let's suppose x1 is a1, b1, c1, or okay, we have it over here in front of us, but I'll just use notations a1, b1 and x2 equal to a2, b2. Now what does this calculation tell us is, when you say x1 transpose x2, this is nothing but transpose of x1, that will be this a1, b1, and this is a2, b2 as it is. So this becomes a1, a2 plus b1, b2. So this is like the dot product of two vectors, right? This is like the dot product of two vectors, a1, a2 plus b1, b2. Similarly, if it had been a 3 by 3 matrix, then the vector would have its dimension by 3. So it would be a1, a2 plus b1, b2 plus c1, c2. Similarly, for n dimensions, it will just carry on, right? So basically, this transformation or this calculation x1 transpose x2 means that we have to find out the dot product. Now, if we observe here, one way would be to obviously do the calculation and find out what are the eigenvalues and eigenvectors. You can find the eigenvalue by the characteristic equation or by the properties. But here you can observe that this is a symmetric matrix, right? This is a symmetric matrix. Now, whenever you have a symmetric matrix, for a symmetric matrix, the eigenvectors corresponding to distinct eigenvalues are orthogonal. Alright, so for any symmetric matrix, the eigenvectors corresponding to distinct eigenvalues are orthogonal. So we are having over here that there are two eigenvalues lambda 1, lambda 2, and then it is a symmetric matrix. So quite clearly, if x1 and x2 are the eigenvectors which are corresponding to these eigenvalues, they will be orthogonal. And for any orthogonal vectors, for any pair of orthogonal vectors, the dot product is always 0. So the answer for this question is 0. The dot product will be 0. Alright. One of the eigenvectors of this matrix. Okay, so it's a simple 2 by 2 matrix. We have to find out the eigenvector, right? So to find out the eigenvectors, first we have to find out the eigenvalues. So how do we find out the eigenvalues? So let's try to do the properties. So what will be the sum of the eigenvalues? In this case it is going to be 1. And what will be the product? Product of eigenvalues, it is going to be minus 30 plus 18, that is minus 12. So sum 1 and product minus 12. What are the eigenvalues? Quite clearly 4 and minus 3. Eigenvalue should be 4 and minus 3. Be careful, sum should be plus 1, product is minus 12. So the eigenvalues are 4 and minus 3. So these are the eigenvalues. Now let's do it one by one. So we have to find out the eigenvector. What we do is go back to the definition, that is Ax equal to lambda x, and just rewrite it as A minus lambda I times x is a 0 vector. Alright, not 0 vector. So now we'll try to plug in these values 4 and minus 3 one by one and find out which of the options is satisfying the answer. Alright, so we'll first try with 4. So what is matrix A? It is minus 5, 2, minus 9, 6. So it's minus 5, 2, minus 9 and 6. And remember, we are going to do A minus lambda I. Lambda is 4. Lambda is 4. So this is calculation for lambda equal to 4. So I'll do A minus lambda I. So that turns out over here as this. Times, let's suppose vector x is x1, x2. And so this is 0, 0. So this is minus 9, 2, minus 9, 2, x1, x2 equal to 0, 0. So we end up with an equation that is minus 9x1 plus 2x2 equal to 0, or this is 9x1 equal to 2x2. So this is what x2, can I write it out as 9 by 2 x1, right? x2 will be 9 by 2 x1. So now let's quickly check the options. x2 is 9 by 2 x1. So that means that if x1 is 2, x2 should be 9. So we don't have any option. There is one option over here, but it is 9 and minus 2. Alright. So this is not the eigenvector. Don't be confused with that. So we have another eigenvalue which is remaining, that is minus 3. So let's try to solve it with that. So we'll now solve for lambda equal to minus 3. What is the matrix? Matrix that we have is minus 5, 2, minus 9, 6. Minus 5, 2, minus 9, 6. And then we are doing minus lambda I. So this will become plus 3. Let the vector be x1, x2 again. And then this is 0, 0. Right? So what are we going to have? Therefore, so this is minus 2, 2, minus 9, 9. x1, x2 equal to 0, 0. So what is the equation that we get? Minus 2x1 plus 2x2 equal to 0, or you write minus 9x1 plus 9x2 equal to 0. Both ultimately give us x1 equal to x2, which means if x1 is 1, x2 will also be 1. Let's check if there is any option for that. Alright, so there is this option 1, 1. So this will be the answer. Alright, so this is a question where we have solved completely to find out the eigenvector of a matrix. Right? So just understand the process. It is quite easy to follow. Try to get x2 in terms of x1 or the other way around, and then check the options carefully. Alright. Okay. Now there could be a case where they don't give you 1, 1, but they could have given you something like 4, 4 or 5, 5. So all those are eigenvectors of this matrix. Alright. All those will be eigenvectors of this matrix. So it's not hard and fast that it should be 1, 1. It can be any vector which has both its elements equal. That will be an eigenvector associated with eigenvalue minus 3. That is what you should remember. So in fact, there is a property which goes like, if x is an eigenvector of a matrix associated with eigenvalue lambda, then any k times x is also the eigenvector associated with eigenvalue lambda. Alright, obviously k should not be equal to 0. So if x is an eigenvector, then kx is also an eigenvector. K should not be equal to 0. K can be any scalar. Alright, so let's do another one. For the matrix A 5 3 1 3, one of the normalized eigenvectors. Okay, so here we have to find out the eigenvector in normalized form. So just the extension of the previous one. So I think all of us should be able to do it together. So try doing along with me. So we'll try to do it again with properties. First find out the eigenvalues. So the sum of eigenvalues should be 8. Product. So what is the determinant? It is 15 minus 3, that is 12. So sum 8 product 12. What are the values? 6 2. Correct? The values are 6 2. And what we are going to do now is a minus lambda I x equal to 0. This is what we are going to do. Do it one by one for 6 and 2. Let's see what do we get. So first lambda equal to 6. What is the matrix? 5 3 1 3. Matrix is 5 3 1 3. So 5 minus 6, 3, 1, 3 minus 6. Assume the vector to be x1, x2. And then right hand side is 0 vector. So this becomes minus 1, 3, 1, minus 3. And so x1, x2 equal to 0, 0. So what equation do we get? Minus x1 plus 3x2 equal to 0, or x1 equal to 3x2. x1 equal to 3x2. So let's quickly check if there is an option for this. x1 equal to 3x2. So whatever is the second element, the first element should be 3 times of that. Option C looks close, but it is not. Alright, so this is 3 and minus 1. Had it been 3 and 1, yes, possibly that was the eigenvector, but now it is 3 and minus 1, so that is not the case. So we'll go on to the next eigenvalue. What was the next eigenvalue? That is 2. So for lambda equal to 2, the matrix was 5 3 1 3. So this will be 5 minus 2, 3, 1, 3 minus 2. Take the vector as x1, x2. So now what we'll have, this becomes 3, 3, 1, 1, x1, x2 equal to 0, 0. And what equation do we get then? So this is 3x1 plus 3x2 equal to 0, or even the other one would eventually give us x1 equal to minus x2. x1 equal to minus x2. So let's quickly jump to the options. So do we have anywhere where both the elements are just minus of each other? So that is happening at option B. So look closely. Option B is the one in which it is happening. And okay, so the elements are taken as 1, 1, and it is the normalized eigenvector that we are asked, right? So if it is 1 and minus 1, so if the vector is taken as 1 and minus 1, so if 1 and minus 1 is a vector, so if 1 and minus 1 is a vector, then how do we normalize this? So if suppose this is x, then what is magnitude of x? It is root of 1 square plus minus 1 square, that is nothing but root 2. And so normalized form of eigenvector will be 1 by root 2 and minus 1 by root 2. That is what they have done. In fact, I think all the options they have given is normalized vectors itself. Yeah, they have given normalized vectors in all of them, but the correct option is option B. C was looking close, but had it been 3 and 1, so yeah, so there that magnitude also turns out to be root of 10, right? So 3 and 1 was also the answer, but that is not the case over here. So the answer will be option B. Thanks for watching. If you like the content presented in this video, do hit the like button And if you haven't yet subscribed to our channel, do subscribe and hit the bell icon so that you get notified about the new videos. Thank you.